We're going to look at this definite integral, and let's start with actually a step 0, which is to identify the pieces. Looking at this pattern, the definite integral from a to b of f of x dx, it helps to identify what is our b. So b in this case is equal to 1. What is our a? A in this case is equal to 0. And what is our f of x? F of x is whatever is inside the definite integral sign. So our f of x is u times the cube root of u plus the fourth root of u. Actually, this du shouldn't be there. Notice that we're actually looking at f of u du and not f of x dx, but that doesn't change anything about the process. Now I put here step 0a. I'm going to also propose a step 0b, which is we can ask ourselves, should I simplify? And that's sometimes a matter of taste. But when you're in this situation where you're dealing with power functions, the power rule is so useful that if you can get it to where it's a sum of power functions, it is. Multiplication is really messy when it comes to antiderivative. So what we'd like to do here is distribute. And before we distribute, it would be helpful to rewrite this as u times u to the 1/3 plus u to the 1/4. When we do that, this is actually equal, the u we could rewrite as u to the 1. We could distribute this through as u to the 1 plus 1/3 plus u to the 1 plus 1/4. And if we get a common denominator and simplify, we have u to the 4/3 plus u to the 5/4. So my suggestion is to take this integral that we have and rewrite it. So I can rewrite this as the definite integral from 0 to 1 of u to the 4/3 plus u to the 5/4 du. And so step 1 is to find the antiderivative. Here we will be using power rule. So power rule for antiderivative says that if you start out with, in this case, it would be u to the n. When you take the antiderivative, you end up with 1 over n plus 1 u to the n plus 1. This works as long as n is not equal to -1, because that ends up with 0 in the denominator and blah, blah, blah. So let's keep going. So what that means is u to the 4/3 will become 1 over 4/3 plus 1 u to the 4/3 plus 1. And I'm going to need to simplify this a little bit. Let's look at 4/3 plus 1. 4/3 plus 1 is equal to 7/3. 1 over 7/3, that's equal to 3/7. So this u to the 4/3, when I take the antiderivative, becomes 3/7 u to the 7/3. Similarly, u to the 5/4 to 4 over 9 u to the 9/4. So the antiderivative of u to the 4/3 plus u to the 5/4 becomes 3/7 u to the 7/3 plus 4/9 u to the 9/4. So we found the antiderivative, which we call big F, and it's 3/7 u to the 7/3 plus 4/9 u to the 9/4. The final step is we evaluate and subtract. What we've been calling step 2 would be f of 1 minus f of 0, which is 3/7 1 to the 7/3 plus 4/9 1 to the 9/4. And that's all going to be minus, well, wait a minute. Okay, you're going to see in a second that sometimes you can skip this step, because if I have 3/7 u to the 7/3 plus 4/9 0 to the 9/4, looking at this, okay, 0 to the 7/3 is 0, 0 to the 9/4 is 0. So this thing I'm subtracting off becomes 0. And then check this out. 1 to the 7/3 is 1, which is 1 times anything, that whatever we multiplied by. 4/9 times 1 here is 4/9. So this answer becomes 3/7 plus. Now, if you do this in the computer, which you totally can, totally take this, I'm going to change the variable from u to x. I can do integral from 0 to 1, f of x dx. It gives me this wacky looking number, 0.873015873. So, I mean, if I just put this into the computer, I get this wacky number, 0.87301587316, like some kind of phone number in an 80s pop song. You know, although if you're observant, this does repeat, which tells me that this is a rational number, because rational numbers have repeating decimal. When we did this in the exact way, we got 3/7 plus 4/9, and it turns out that's the same number. And I think that 3/7 plus 4/9 looks so much more aesthetically pleasing than this. Well, that's how we do that problem, and that's the insight we gained from it. Big trick here that I want to re-emphasize is that to get at this, we have to start with algebra.